So I'm going to start chapter 10.4, multiple regression, with a really quick review of simple linear regression, which is a statistical technique for finding the best fitting straight line for a set of data. It's used for making predictions. The independent variable is also called a predictor or explanatory variable. The dependent variable is also called a criterion or outcome variable. The linear relationship can be explained by this equation, which we're familiar with. Y hat is equal to beta naught plus beta 1x, where beta naught is the y-intercept, beta 1 is the slope, y hat is the outcome variable, and x is the explanatory predictor or independent variable. Remember the best fit line through a set of scatter. These we try to minimize the distance between each point and the fit line. This distance is called a residual, also called error. So when SPSS, we go to analyze regression linear, we bring over our dependent variable, bring over our independent variable, and we go through these steps. We talk about plots, we look at, first we do statistics, estimates, confidence intervals, model fit, descriptives, then we do plots. We do this crisscross and we get the Z residuals and the Z predicted. Then we go to save, we look for cooks, and then we check our assumptions. All right, so we want to see that our standardized residuals are not more or less than plus or minus 3. We want our cooks to be less than 1. And so we evaluate our output like we do, and we look and make sure that everything's fine. And then we get our model summary, which tells us our R and our R square, which is the coefficient of determination, which tells us 52.7% of the variation in BMI can be predicted by the percent body fat. Here is our F statistic. We have a significant prediction. And then we get to the coefficients. This is our y-intercept. This is our slope. We check our standardized residuals. We have a little problem here, but we'll just keep going. And then we're less than 1. Okay, so then we state our null or alternative hypothesis. Percent body fat does not predict BMI. It does predict BMI. We set our alpha is always equal to 0.05. We just did this, calculate the test statistic, and we state our conclusion. Findings indicate that percent body fat is a significant predictor of BMI. We write it out like this. Approximately 52.7% of the variance in BMI can be attributed to percent body fat. Examining the predictor, we see that body fat is a significant predictor of BMI, and we give our T statistic and our confidence interval. And then we can write out our prediction equation and calculate for any new X. We can find out the BMI. Okay, so that was quick, but now we're going to go into multiple regression. This is when you add a second or third independent variable to the equation. All right, we've seen this VO2 max data set before. I'm going to just read the scenario really quickly. A health researcher wants to be able to predict maximal aerobic capacity, VO2 max. We already know this data set. An indicator of fitness and health. Normally, to perform this procedure requires expensive lab equipment and necessitates that an individual exercise to their maximum, i.e. until they can no longer continue exercising due to physical exhaustion. This can put off those individuals who are not very active or fit, and those individuals who might be at higher risk of ill health. For these reasons, it's been desirable to find a way of predicting an individual's VO2 max based on more easily and cheaply measured attributes. To this end, the researcher recruits 100% participants to perform a maximum VO2 max test, but also records their age, weight, heart rate, and gender. Heart rate is the average of the last 5 minutes of a 20-minute, much easier, lower workload cycling test. The researcher's goal is to be able to predict VO2 max based on age, weight, heart rate, and gender, and use all variables. So we have new vocabulary. We talked about this before. Outcome, target, criterion is the dependent variable. The predictor, explanatory, or regressive variables is the independent variable. It doesn't matter which of these you use. I'll try to be consistent and say DV and IV, but I might accidentally say the others. So a possible research question would be, do age, weight, rate, heart rate, and gender predict VO2 max? The reason we do this is because we can control for one variable statistically as we evaluate the others. So we put them all into the equation, and we can hopefully account for more of the variation in the dependent variable by using more independent variables. So now we just extend. Before we just had the B1x1, now we have B1x1, B2x2, B3x3, etc. So we have the intercept, age, weight, heart rate, and gender. All right, so really quickly, there's this thing called dummy coding. We'll come back to this, but when you use a categorical variable as a predictor, like we do in gender, right? We have 2 levels of that variable. You need to have one less variable than the number of levels you have in your categorical variable. So like I said, gender has 2 levels, male and female. So we need only one gender variable with males as 1 and females as 0. We could do it the other way, but this is the way we have it in this particular data set. The constant will represent females and the slope will represent males. So as we go from 0 to 1, we will add or subtract depending on the slope. If we were looking at political party with Democrats, Republicans, and Independents, we would need 2 variables. One for Democrats equals 1 and all the others is equal to 0. And another with Republican equal 1 and all else equals 0. And then we would just leave off the one for independents. And that would make the reference category be the independents. We wouldn't put in the variable that has everything. Democrats coded as 1, Republicans coded as 2, and independents were coded as 3. It wouldn't work. So you would recode these variables. We're not going to do it in this data set. We're just going to use gender, which is already coded for us. And I'll come back to this when I explain how to interpret the output. Okay, so same thing, analyze regression linear, bring over the VO2 max. Now I've put everything in the variables. I click on, everything into the independent variable box. I click on statistics, I do estimates, confidence intervals, model fit, descriptives, and now we want to ask for this collinearity diagnostic, and we'll also ask for this Durbin-Watson. Then we click on plots and we do the crisscross again, Z-RZ, Z-predid, and we ask for histogram, probability plot, and we're going to also ask to produce all partial plots. Then we go to the save button and we just ask for cooks again, and then we start to evaluate our assumptions. There is a little bit of a pattern here. I would say I see a little bit of a curvature, but we're just going to say everything's good. We're between plus and minus 3 up and down, so we'll keep going. Homoscedasticity is the technical term when you're doing multiple regression for equal variances. We can say it's robust to violations, go find a citation, and keep going. Now we're going to look at the partial regression plots. They show the linear relationship between the dependent variable and each of the independent variables. And so we see kind of a linear relationship, definitely here for age, and definitely for heart rate. It's not a very strong, but it's a linear relationship. And you don't need to evaluate the partial plot for categorical independent variables. You also want to check that you don't have any correlations here that are greater than 0.7. And so we see that we don't have any that are that large. Variance inflation factor of 1 indicates that there's no correlation between a given predictor variable and any other predictor variables in the model. So when we ask for the collinearity diagnostics, we get tolerance and VIF. VIF, 1 over VIF is tolerance, so these are related. Anything larger than 10 for VIF would be problematic, but we don't have that here. We're just going to look at the histogram, and we're going to call this normal. And then we'll go to our model summary. One thing you see now, we have this adjusted R square. So we have R, and then R square, and then an adjusted R square. And as you square it, obviously we have 57.7 here and 55.9. There's an adjustment that we do when you add more predictors into the equation, because even if you add bad predictors in the equation, your R square is going to go up. So SPSS calculates this adjusted, and this is the one we report for multiple regression. So now 55.9% of the variation in VO2 max can be predicted by age, weight, heart rate, and gender. This Durbin-Watson, we want it to be around 2. There's no autocorrelation. Autocorrelation is when you have time series data. So say you're looking at the stock market every day, you're looking at the same thing over and over and over again. So it will be correlated with itself. Same with attendance in a room or other measures where you're looking at the same thing repeatedly over time. These are not auto-correlated, so it's not a problem. And I just wanted to show you that we don't always have to ask for the Durbin-Watson. If you know in your design that you don't have repeated measures, then you're fine. So now our degrees of freedom are 4 and 95 because we had 4 predictors in the model, and then we use the residual. So we say F of 495 is equal to this statistic here, 32.4, p is less than 0.01 rather, adjusted r-square is 55.9 or 0.559. And then we go to our coefficients, and you see here we have the constant, and then we have the slope for each of the predictors. So age was negative, weight was negative, heart rate was negative, and gender is positive. So what does this mean? So holding everything else constant, so not considering weight, heart rate, and gender, for every unit increase in age, I would subtract this much from this constant, and that means that our VO2 max would go down by this slope. For every unit increase in weight, my VO2 max goes down. For every unit increase in heart rate, my VO2 max goes down by that amount. And then here's the tricky part. For every unit increase in gender, well, we only have 2 levels of gender, so females are my reference category, and they have a VO2 max of 87.8. But as I go from 0 to 1, so from females to males, I would add, because this is positive, that value to 87, and so men have higher VO2 max than the females. I have to, before I even start interpreting all these, I want to make sure everything is significant, which it is here. Here are my confidence intervals, here are my t-statistics. Our residuals are fine, and our Cook's D is fine. So I just went through the interpretation, and again about the dummy variable. So for every unit increase, we go from 0 females to 1 males, we add. And so here I'm going to state the conclusion. Findings indicate that age, weight, heart rate, and gender significantly predict VO2 max, and I write out my F statistic, approximately 55.9% of the variance in VO2 max can be attributed to these predictors. Examining each predictor, we see that age is a significant predictor of VO2 max, and then I write that out. Weight is, heart rate is, and gender is also. Okay. And then for the prediction equations, in order to do this, you've got to go back to the coefficients table, and so each of these are the slopes, right? So I'm going to go into the next slide. Now let's imagine that we wish to predict someone aged 30 years old, weighing 80 kilograms, having a heart rate of 133 beats per minute, and male. You would calculate this as follows. Beta naught, beta 1 age, beta 2 weight, beta 3 heart rate, and beta 4 gender. So I'm going to take each of these are our betas, see, beta. So I say 87.83, which is the constant, minus, because this is a negative, 165 rather, that's this beta, times age, which we haven't put in yet, minus, because this is also negative, parentheses, 0.385 times weight, minus, also because this is negative, same thing, plus 13.208 times gender. So now let's plug it in. 30 years old times 30, 80 kilograms times 80, 133 beats per minute times 133, and then male is the ones. And we calculate all that out, and we get 49.59 is our predicted VO2 max.